Welcome to Unit 5, Video 3, Empirical and Molecular Formula. By the end of this video, you should be able to understand the difference between an empirical and a molecular formula. You should be able to determine the empirical formula when given the molecular formula. And you should be able to determine the empirical and molecular formula from lab data. Let's start by defining empirical and molecular formula. An empirical formula is the lowest whole number ratio of elements in a compound. Take, for example, the compound CH4, or methane gas. This is an empirical formula. It tells us that for every one carbon atom, we have 4 hydrogen atoms. This is the smallest whole number ratio. But not every molecule exists in the smallest whole number ratio. Therefore, we have something called the molecular formula. This is the actual formula of the compound. If, for instance, the compound doesn't exist in the smallest whole number ratio, like maybe C2H8. Here, we have 2 carbons for every 8 hydrogens. Therefore, this is not the smallest whole number ratio. This is a molecular formula. It is possible for the molecular formula, the formula of the actual compound, to be the same as the empirical formula. CH4, for example, which we already looked at. That's the formula for the molecule, but it's also the smallest whole number ratio. Water, H2O, is another example. H2O is the smallest whole number ratio, so it's empirical, but it's also the formula for the molecule. Empirical means lab data. Therefore, we can get ratios from lab data empirically, but we need a little bit more information to get a molecular formula. Let's look at some molecular formulas and try to determine their empirical formulas. First, some examples. Here we have the molecular formula H2O2, which reduces to the empirical formula HO. Again, C2H4 becomes CH2. C6H12O6 has the common denominator of 6, so we can divide through and get CH2O. Here's some to try on your own. Pause the video here. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice there are 2 examples here where the empirical formula and the molecular formula are the same. Here, the actual molecules exist in the smallest whole number ratio. Since empirical formulas are based on lab data, let's try calculating some empirical formulas from some lab data. In order to do that, we first want to obtain the mass of each element present in grams. So we can do this a number of different ways. We're going to do this in lab, but there's a ton of different ways to do it. Then we convert the masses to moles of each element. Then we divide by the smallest number of moles to convert the smallest number to 1. This will give you integers and help you determine the ratio between moles of elements. This is something we did before when we looked at percent composition. And finally, if you divide by the smallest number and you get something that's not a whole number, you need to multiply so you get whole numbers. You can't end up with a formula with a fraction or a decimal in it. Let's look at an example. Here in lab we find that 4.15 grams of aluminum and 3.692 grams of oxygen make up a sample. In order to determine the empirical formula, we need to determine the smallest whole number ratio of atoms of aluminum to atoms of oxygen. We can do this by determining the smallest whole number mole ratio between aluminum and oxygen. We can't do it by looking simply at the mole ratio of grams, or at the ratio of grams of aluminum to grams of oxygen, though. So let's start by converting each of these values to moles. Using a conversion factor, that has the atomic mass of aluminum from the periodic table, or the mass of 1 mole of aluminum from the periodic table, we find that the sample contained 0.1539 moles of aluminum. Repeating this process with oxygen, we find that the sample contained 0.2308 moles of oxygen atoms. This does give us a mole ratio. From here, we could theoretically write the formula as Al 0.15939, O 0.2308. This is the ratio between aluminum and oxygen. However, this is a problem for 2 reasons. First, it's not a whole number ratio, as the definition tells us we need. And second, if we think about aluminum oxide on the atomic scale, if we had 1 molecule of aluminum oxide, that would have to contain 0.1539 atoms of aluminum for every 0.2308 atoms of oxygen. And that just doesn't make sense, since we can't divide atoms into smaller pieces. So how can we get rid of these decimals? Well, we can divide each of the values by the smaller of the 2 numbers, in this case, 0.1539. So 0.1539 divided by 0.1539 gives us 1, and 0.2308 divided by 0.1539 gives us 1.5. Again, from here, we could theoretically write our formula as AlO 1.5, because for every 1 aluminum, we have 1.5 oxygens. But this is problematic for the same reasons we discussed above. So we need to turn this into a whole number ratio. So how can we turn 1 to 1.5 into a whole number ratio? Well, we can multiply each by 2. 2 times 1 is 2, and 2 times 1.5 is 3, giving us a ratio of 3 oxygen atoms for every 2 aluminum atoms, or 3 moles of oxygen for every 2 moles of aluminum. And it gives us an empirical formula of Al2O3. We can also do this if we're given percent composition data, like we were in the previous unit. Here we find that 25.9% of a sample is nitrogen, and 74.1% of that sample is oxygen. We can repeat this same procedure by making one important assumption. If the sample is approximately 26% nitrogen and 74% oxygen, it doesn't really matter how much of the sample we have, because the percentages will always be the same, as we saw in the previous unit. So let's just assume we have 100 grams of the sample. That will make our math really easy. In 100 grams, we would have 25.9 grams of nitrogen and 74.1 grams of oxygen. So, again, we're going to convert to moles using the conversion factor. And we find that we have 1.85 moles of nitrogen, and we have 4.63 moles of oxygen. In order to turn this ratio into a whole number ratio, we can divide by the smaller of the 2 values. 1.85 divided by 1.85 is 1, and 4.63 divided by 1.85 is 2.5. Again, this would give us a formula of NO2.5, which doesn't make sense, so we can multiply by 2 to get N2O5. Finally, if we want to determine the molecular formula of a compound, we're going to need a bit more data that we can't collect in lab. We don't have the materials to do it. We would need a mass spec machine, which is a very expensive, very delicate piece of machinery. But we can determine the molecular formula if we have the empirical formula and we're given the molar mass of the molecule. So the molecular formula, as we've seen, must be some whole number multiple of the empirical formula. Here, we have the empirical formulas, and the molecular formulas are all whole number multiples. Therefore, their masses must also be whole number multiples of the mass of the empirical formula. Therefore, we can use that information to determine the molecular formula. Take this example. Here we're given an empirical formula of CH4N and asked to determine the molecular formula. First, let's calculate the molar mass of the empirical formula. We have 1 carbon, 4 hydrogens, and 1 nitrogen, so together we get an empirical formula mass of 30 grams per mole. Now we can divide the molecular molar mass by the empirical molar mass. And we see that our molecular formula must be twice our empirical formula, since its mass is twice that of the empirical formula. Multiply your empirical formula by 2, and you get C2H8N2 as your molecular formula. Here's a problem to try on your own. Pause the video here and see if you can work through this problem. First, you're asked for the empirical formula, and once you've determined that, you're asked to convert it into a molecular formula. Welcome back. Here's what you should have gotten. An empirical formula of zinc oxide, 1:1 ZnO, and a molecular formula of Zn3O3. That brings us to the end of our video. Let's review our goals. First, we looked at the difference between an empirical formula and a molecular formula, empirical being the smallest whole number ratio of atoms in a compound, whereas the molecular formula is not necessarily the smallest whole number ratio, but it does represent the actual ratio in the compound. Then we looked at how to determine the empirical formula from the molecular formula. And finally, we looked at how to determine the empirical and the molecular formula from lab data.